Alright, so in this video I'm going to cover the exam 4 review for Dr. Buchanan's Statistics for the Social Sciences class. This is using the Nolan and Heinzen Statistics for the Behavioral Sciences book and the 6-step hypothesis testing procedures for correlation, regression, and 2 types of chi-square. So for the first example, let's do correlation. So we're going to start by looking at math ability. And so you hear a lot when you teach a statistics course that, oh my god, I'm not good at math. And then I just sigh heavily because math and statistics are cousins, but not necessarily related. And so we're looking at actual math ability and belief that math ability is innate. So this idea that some people are just good at math. All right. And so I have the scores on the next slide, or you can use the scores from the handout on Blackboard. So we're going to make a scatter plot of the scores, describe the pattern of the association, and then test if there's a significant relationship between math ability and innateness belief. And we're going to use 0.05, right? So first step, here's the data. Remember that each person gets their own row. So this is one participant who has a math ability score and a belief score. And then we are going to have 6 people overall. So N is 6 in this study. Okay. So first thing I did in SPSS was make a scatter plot. So you can watch the video on how to make scatter plots. Or if you watch the correlation in SPSS video, it also shows you how to do scatter plots. And this really helps you look at like what should the correlation be. And this one's kind of clearly negative. So it leans to the left. And then as belief goes up, math ability goes down. So the more you believe that it's an innate feature of people, the less likely you are to have a high math score, because you believe it's innate, it's someone else. So you're not going to, when you get frustrated, you stop working and stop trying. You can also add the line of best fit just to help yourself see that pattern if you're not very good at looking at these graphs. And it also will help us talk about homoscedasticity. So how far are the dots away from the line of best fit? So to describe that pattern, I would say that it is negative. And it's a fairly strong relationship because, let me back up a slide, most of the dots are very close to the line. Okay. So that's pretty close. Now when you're thinking about how close together they are, remember that the scaling matters. So the larger the scale, and the dots are far away, that's further away. So this scale is not very large, so this dot is actually not that far away. Okay. So it's a strong negative relationship, which means that as belief goes up, increases, math ability decreases. And I can't say that that's causal. It's also true that as math ability increases, belief decreases. So it can go both ways. All right, so let's do the 6 steps for correlation. So step 1 is always our assumptions. So first assumption is that the DV and the IV have to be scale variables. I don't have a whole lot of information about them, but it looks like they are. And so they're at least interval. Math ability is probably ratio, and belief is probably on one of those 1 to 15 maybe scales. And so I'd say that, yeah, they're at least scale, which is interval or ratio. Then the next question is it normal? Well, I don't have at least 30 people, so I can't assume normality, so let's say no. The third one is random selection. Since we're talking about people in general, I can't do that really. And the fourth one is your Scrabble word, so homoscedasticity. And I would say it's pretty close, right? So you want most of the dots to be evenly spread across the line. So let's see here. This is the furthest dot out here, and this is the furthest dot out here. And so that spread is roughly equal. That's a little harder with only 6 or 7 points, but, you know, give it some slack, and I would say, yeah, it's good. Okay. So those are assumptions. Step 2 is to talk about what are the 2 variables that we're correlating. So I've got math ability and belief. And we want to talk about, let's do research in the null here, that R is not equal to 0, so it is something greater than or less than 0. And remember, we're implying that 0 is rho. So we're saying that R is not the population correlation, but the population correlation is usually assumed to be 0. For the null hypothesis, we're saying that R is 0, that there's no relationship between the two variables. Okay, so the first one is that there is a relationship between the variables, and the second one is that there's no relationship between the variables. Step 3, so I ran this in SPSS. Now remember that it gives you this line here, which is correlated with itself. And so you either want to look above or below that line of ones. Be sure you come across from Pearson correlation and you don't use either of these things. So this is R here. So R is negative 0.92 if I round up. And that is a strong negative correlation. Remember that 0.1 is perfect. 1 is perfect. So a negative 0.92 is a pretty strong correlation. Now, for step 4, we need the degrees of freedom. So degrees of freedom is n minus 2, 1 for x, 1 for y. So there are 4 degrees of freedom. We use a two-tailed test because we did equal to and not equal to. And I'm going to use 0.05 because the problem told me to. So I'm going to come across here at 4. And so it's plus minus 2.776. So plus and minus 2.776. Step 5. Now, you can calculate this by hand by using this formula. That's an n. Try again. Okay. So plugging that in is negative 917 divided by the square root of 1 minus negative 0.917 squared. So that minus sign will go away, divided by 4. That's degrees of freedom. Okay. So if you math all of that out, it essentially ends up being negative 0.917 divided by 0.20. Think if I can read my own scribbles correctly, but it comes out to be negative 4.58. And so the main key is to make sure that you're doing exponentials first, and then the subtraction, division, square root. So doing it in the right mathematical order. If you are one of those I'm not good at math people, you can use MOTE. Okay. So make sure you enter the correlation coefficient, the sample size or degrees of freedom, and then I got roughly the same number down here. It's a negative 0.460, and that's just a rounding error. Okay. So that's T found. So step 6 is, do we reject the null? So I've got 2.776, and then 2, that's a positive one, sorry, 2.776, this is the negative side, so reject is out here in the tails, and fail to reject is out here in the middle, and we're way over here at negative 4.58. So we would reject the null. There is a significant relationship between math ability and belief that it is innate, such that as math ability increases, belief decreases, or the other way around. As belief increases, math ability decreases. Okay, so that's correlation. Moving on, let's do regression. Possessed slides. There we go. All right. So, a cognitive psychologist, sometimes when you use books examples, they don't properly use words, conducted a study of whether familiarity of the words predicts the time it takes to indicate whether a word is single or plural. And so, everybody's given that same set of words. Familiarity is rated on a 7-point scale, so the higher the better. And then my response times are on this slide. So here for participant 1, this is how familiar the word is, and this is how long it took them to respond to the word. Participant 2, etc. So we've got 7 people in this study. Okay. So the first thing we're going to do is write out the regression equation. Look at if familiarity predicts response time. So remember, it's always X predicts y. And then we will test that with our 6 steps. We'll look at the response time for a person who has a familiarity rating as 5. So this is where we say x is 5. And a scatter plot. So let's do these 3 first, because they're the easiest ones to kind of knock out with a graph. So I entered all this into SPSS and came out with this scatter plot. So I've got, make sure from your x variable actually goes on the x-axis and y goes on the y-axis. It does matter in this one, otherwise you will get the wrong regression equation. So here's the equation. It's 4.04 minus 0.48x. So for every 1 unit increase in familiarity, we're losing the reaction time or response time is going down, which makes sense. More familiar words should be faster. And that's what we see in this picture, that as words get more familiar, response time goes down, which is a pretty common effect in psycholinguistics, where people who recognize words faster that are more familiar. So that equation was y equals 4.04 minus 0.48x. You can get that from the graph, or you can run this in SPSS and look at that output too, which we will do here in a second. I'll show you where you can find these numbers. So score for a person who rates familiarity as 5. That's going to be here, so I'm going to fill in 5. So y equals 4.04 minus 0.48 times a fairly familiar word. If you do all of that out, it's 1.64. That's a response time. So the response time is, that's 1.64 seconds, okay, which is pretty quick. Okay, so now let's see if that relationship between familiarity and response time is statistically significant. So does it actually predict? So starting with our assumptions. Okay. Let's do, the first one is the DV and the IV are they both scale variables? Yes. So response time is a ratio variable. In theory, it could be 0. Probably not, but it could be. And familiarity is a 1 to 7, so that's an interval scale, so they're both scale variables. Is it normal? Probably not. I got less than 30 people. Response times tend not to be normal as well. They tend to be positively skewed because there are lots of fast times and then a couple people are usually pretty slow. Can I randomly select? Yeah, no. Okay. Especially if we're just working with people in any particular language, that's going to be kind of hard to randomly select from the population. And then the last one is homoscedasticity. So I'm going to back up to my graph here to look at that one. Okay. So most of the dots are fairly close to the line. So if I drew a line across the furthest dots, that spread is roughly equal all the way across. So I would say yes, homoscedasticity is also met. Okay. So that's it for the assumptions. In step 2, what I'm going to do is I'm going to say we're going to test familiarity as it predicts response time. Okay. And so you could say familiarity predicting response time. This is just kind of a quick and easy way to do it using this little arrow. And so I want to say that again. So familiarity predicts response time. For my research hypothesis, I want to say that B value, or beta, is not equal to 0. Right, so we're testing if the slope value is significantly different from 0. It could be negative, could be positive. In this case, it's going to be negative. But we want it to be different from chance, which is 0 or nothing. Okay. So here I would say beta is 0. You can also do B is not equal to 0, B is equal to 0. Remember that B and beta are the same idea of a slope. It's just that beta is standardized and B is not. Okay. All right, so same structure as correlation, equal to and not equal to. All right, now if I run this in SPSS, I get the option here to look at beta, so standardized coefficients. So I'm going to list beta, 0.97. But I'm going to take a quick second to talk about this here. If it'll let me. There we go. So if you're asked to write out the regression equation and you don't do the graph, you can also get it from here. They're in alphabetical order under B here, where this one's A and that one's B. And so I would write that y is 4.04 minus 0.48x. Should be familiar since we just did this one. But here where it says constant, that is A. Where your variable name is, that's B. I know they're both listed under B here, but that's just kind of a misnomer or mislabeling in SPSS. All right, for step 4, we need degrees of freedom. It's still n minus 2, so 7 minus 2, so df is 5. We're still using a two-tailed test for everything. So I'm going to go 5 over here, and the problem said to use 0.05. So plus m minus 2.571. Okay, so remember, everything over here is plus minus. Step 5, now you could still use that same formula for t, but gosh, why would you go through all the trouble when you could just use this number here? Do not use the constant line. I do not want to test if the constant is different from 0 in this particular question. I want to know if the familiarity predicts response time, so I want to use this t here next to that. So use the one next to beta. So t is negative 8.70. So a big T value. And I definitely am going to reject, but let me show you. So I got 2.571, 2.571 negative. All this out here is reject. Okay, this in here is fail to reject. And then we are way over here in space at negative 0.87, so I'm definitely rejecting the null. And so what does that mean? Well, if I reject this null, that means that familiarity does predict response time. So if I know how familiar someone finds a word, I can use that to determine how fast they're going to respond. Okay? So for every 1 unit of familiarity, I get 0.48 units negative response time. So let me back up a second. So a couple more here. So B here, the interpretation of that is like every time familiarity goes up, response time goes down. Okay, so that's it for correlation and regression. Now we're going to move on to chi-square, so there's a little bit of non-parametric statistics. Remember that non-parametric statistics have different types of assumptions and different types of DVs. So we've got this superintendent who is looking at moving around the resources for physically impaired students, looking at the distributions of where those students are located. So we've got 5 schools and 20 students each, and looking at, it gives you all the different information, so we're going to use that to write out the observed box, but in this case we're going to use 0.01. So are the patterns of physically impaired students different across these different schools? All right, so first step is your assumptions. So that first assumption is small n. So to do that, I need to write out my observed box. I'm going to hold off on this one for just a second. And then 0. So we can't have any zeros. And so I'm also going to kind of hold off on those two. So let's come back to these after we've written out the observed box, because we don't have that yet. And so I am looking at the physically impaired students and what school they're at. So I have 2 variables. So that makes this an independence test, because I have 2 variables at once. And then I'm going to do the same thing again here, impaired, and the type of school, or the school they're at. So for my research hypothesis, I'm essentially going to say that my observed values are not equal to my expected values. So what does that mean in this case? Well, what I'm doing is looking at the patterns of students across the schools. So essentially I'm asking, is the ratio of impaired to non-impaired students different across these 5 different schools? Or you can look at it the other way, that are there more physically impaired students at one particular school versus non-impaired students? Okay, so we're asking if the patterns are the same for both variables. And that's why it's an independence test, because I have 2 variables. For this one, it's that the observed and expected patterns are the same. Okay, so they're roughly equal across school. So let's write out that O, statistic I would tell you to pull up the example so I don't have to kind of flip back and forth. But basically we're going to do school 1, 2, 3, 4, and 5. And then impaired and physically impaired and not. So it said that school 1 was 4 and 16, 1 and 19, 6 and 14, 3 and 17, 7 and 13. So that is my observed value. To do my expected values, what I'm going to first do is come up with column totals and row totals. So these are column totals down here, and they're all 20. That makes life really easy here in a minute. And then over here it's 21 and 79. The total number of students is 100. So to create my expected chart for this data set, for cell number 1 here, I'm going to do 21 here times 20 divided by 100. Okay. So that's 4.2. So what I do is 21 times 20 divided by 100. And what's neat is since all of these have the same column total, it's the same formula over and over again. So it's 4.2, 4.2, 4.2, if you'll excuse my scribbles, 4.2. Because it's 21 times 20 for this box as well. For this one that's a 6, it's 21 times 20, 21 times 20. You get the idea. Okay. The same thing is true for the second row, so 79 times 20 divided by 100. So all of these are 15.8. So this total across here should still be 21 within some decimal rounding. This out here should still be 79, and these going down should still total to 20. So your row and column totals and overall N have to match an O and E, and essentially the purpose of calculating an expected frequency distribution is to get what I would have expected given these row and column totals if everything were due by chance. Okay. So you need O and E for step 3. Now that I have that though, let's look at the assumptions. So I have 3 boxes that are less than 5. Okay. So there are 3 of the what is there 10 that are less than 5. But I said at least as long as at least 50% of them are good, we're good. Okay, so that's 70% that are okay. So I would say yes, we meet that assumption, and we don't have any zeros. So yes, we're okay. So essentially we're okay on both of these because we don't have too many small n's and we don't have zeros. All right, that's really messy, but you get the idea. So step 4, now degrees of freedom is sort of weird for this. It's columns minus 1 times rows minus 1. Okay. So that's 5 minus 1 times 2 minus 1, which is equal to 4. We're going to use 0.01 because that's what the problem asked for. And so it's 13,277. Okay. So remember, chi-square gets bigger as you go, as you add more categories, because this is not people out here. Remember, this is not n minus 1, it's columns or categories minus 1. Okay. I used Vassarstat's website to be able to do this. So there's a video on YouTube that covers chi-square on Vassar's website. And so this is their independence test, or they have it listed as contingency table. Same thing. So I entered all of my numbers here. So this is O, essentially. And it calculated everything out for me, so I got the right degrees of freedom. Woohoo! And here's my chi-square. So chi-square is 6.87. And let's see if that's significant. So for 0.01, I had 13.277. I'm rejecting out here. Ooh. Good thing you guys know my handwriting. That is a terrible word, reject. It's fail over here. And unfortunately, I don't even get half that far. So 6.87. So I would fail to reject. So what does that mean? That means that the pattern of physically impaired and not physically impaired students is the same across all the schools. So So there's no relationship between school and impaired, which means there are not more impaired students at one school over the other. Now, effect size is here listed under Kramer's V, or phi. So it is, you can use that symbol or this one. Oops, that's a mess. How about that one? And that is 0.26. So in interpreting its size, we need a chart. Okay, remember that this is DF smaller. So that's rows minus 1. So remember that was 1. And columns minus 1. That was 4. And so that's DF smaller. And so I guess it's close to a medium effect size. So we have a medium effect. So there might be differences between these schools, but we just don't have enough participants to really find that difference. And if you look at the particular numbers, it seems to me like this has the largest ratio of physically impaired students, these two schools, where the other ones are kind of lower. But given this set of data, we can't find that difference, so there's not enough power. All right, so we rejected the null. We said it was a medium effect size. And so there's no differences that we can find between the ratios of physically impaired students across schools. All right, last but not least, let's do an example of a goodness of fit test. Okay. So a goodness of fit test is where I have one variable. And so example similar to the ones we did in class, who's the best professor? And so this time you're looking at ratings for the professor. So you got online at Rate My Professor or whatever it's called now and looked at their ratings. Remembering that those things are highly biased in their selection procedures, right? People tend to love or hate professors. You don't normally get the middle ones. And so we have Professor A with 25 very favorable ratings, 25 favorable ones, 10 neutral, 5 unfavorable, and 4 favorable. Okay. And so you want to know, should I recommend the professor? Well, if they have a higher number of favorable ratings, you would say yes, right? So we want to see if that pattern is the same. So if they have all the same numbers of ratings across favorable and unfavorable, that means that people hate them and love them. So it's kind of a mixed bag. And so you're wanting to know if they have a bias towards one end or the other, right? So are there more favorable ratings than unfavorable? Okay. All right. So for our assumptions, same two, small n and zeros. So let's come back to that in just a second. For step 2 here, since this is a goodness of fit statistic, let's do, it's just ratings. So I want to know if the ratings are different across all these categories. So my research and my null here, I got ratings. Okay. So I want to say that the observed values are not equal to the expected values. There are more ratings in one category over another. And the observed values are equal to the expected values. The ratings are the same across all of them. So for this one, let's draw out O. So we've got 25, 20, 10, 5, and 4. And then let's do E. So what I did for E here is I added up the total number of participants. So 64 people have given ratings. And I took 64 divided by 1, 2, 3, 4, 5 categories and came up with 12.8. So if this professor really was a mixed group where everything was roughly equal and people rated them as both favorable and unfavorable, like completely random ratings essentially, they would have 12 or 13 in each category. Now let's go back and look at those assumptions. So we've got 1 out of the 5 categories are less than 5. So that means that 4 out of the 5 are good. So we're okay because that's 80% of the data is okay. So it's okay. And now zeros, we don't have any zeros, so none. So we're good. It's okay. However you want to word that, it's a little awkward to say zeros equals yes. But the question is, are there no zeros? Yes, so we're okay. Okay, So for step 4, this degrees of freedom is usually listed as categories -1. So we have 5 different ratings, -1, so it's actually the same degrees of freedom, but we're going to use 0.05 this time. So 9.488. Excuse me. So we have to get at least 9.5 points to reject the null. So I used VasterStats one-way chi-square page to do this. And what you do is you enter the observed frequencies here and the expected frequencies here, and it will calculate out everything for you. And then here's chi-square down here. So I got 2709. I can check, make sure I did the right degrees of freedom. So I got 2709. Let's compare that to our cutoff score. So we had 9.488, and then this is out here as reject. And then this over here is fail. So I had 2709, so I definitely would reject the null. So what does that mean? Let me back up a step. Let's look at the observed frequencies here. So they had 25 very favorable ratings and 20 favorable ratings. So those are clearly much larger than the neutral and unfavorable ratings. And so it seems to me as if they have more in the top half and the more favorable categories and less in the least favorable category. So you should like this professor. The cool thing I like about VasterStats is it actually gives you the numbers to figure that out. Now this is not on the test, this is just for you to know. But generally what it does is it calculates how different is it from the expected value. So it actually calculates a z-score of how different is 25 from 12.8. And from a z-score, 0.05 is 1.96. So most people use a criterion of around 2. And so anything that's over or under 2 is considered very different from normal. And so essentially they have way more than you would expect here at the top. These are positive, so more favorable ratings and less unfavorable ratings. Now you can also see that by just kind of looking at the numbers. It's clearly obvious that 25 is bigger than 4. But that's a way that people sort of analyze like which end is better in a statistical way. So what I would say is, would I recommend this professor? Oh yeah, they have way more high ratings than they do low ratings. And we rejected the null, so it is a significant difference between the high and low ratings.